In this video, we're going to continue our work with integration and look at the area trapped between a curve and a line. This is question number 8. In part A, we're asked to sketch the curve y is equal to negative x squared plus 7x minus 6 and the line y is equal to x plus 2 on the same set of axes, showing any points of intersection with the coordinate axis. So let's go ahead. We've got now a quadratic, a parabola, and we've got a linear, so a straight line. This is a negative, so it's going to open downwards, and all we need to do is go ahead and find the points of intersection. So if we look at this, if I set y equal to 0, I could rearrange this and I could write 0 is equal to x squared minus 7x plus 6. That will factor. We will have now x minus 1 and we'll have x minus 6. So from here we'll have a point of intersection at x is equal to 1 or 1, 0, and then we'll have another one just here at 6, 0. This will cross the y-axis at the point 0, negative 6, and we can draw that on. So let's go ahead and do that, and that will be somewhere down here. So my parabola is going to open downwards, and it will look, give or take, something like so. So we'll come up, we'll turn round, like that, and then back through this point just here, and then round like so. So this point is going to be 0, negative 6. The line y is equal to x plus 2, well that's going to just be a straight line. We're going to have now a gradient of 1, and we're going to have a y-intercept here of 2. So this is going to look something like so. So let's just change that very slightly. That does something like that. Not brilliant, it just gives us some idea. We can of course extend this if we want, but that's a rough diagram of it. So y is equal to x plus 2, y is equal to negative x squared plus 7x minus 6. We've got this point of intersection here which is going to be 0, 2, and this point right here which is going to be negative 2, 0. In part B, we need to find the coordinates of the points where the line cuts the curve. So that's going to be just here and just here. For this particular problem, we can set up simultaneous equations. So I'm looking for this point of intersection and this point of intersection. So using simultaneous equations that we've learnt in a previous unit, if y is equal to x plus 2 and y is equal to negative x squared plus 7x minus 6, we can set those equal. So negative x squared plus 7x minus for 6 is equal to x plus 2. If I add x squared to both sides, subtract the 7x, that's going to be minus 6x, and add now the 6, that's going to be plus 8. We can set this to 0. Factor in, we've got x minus 2, and then we've got x minus 4. So for solutions here, we will have x is equal to 2 and x is equal to 4. Substituting into the linear to find the y coordinates, we've got y is equal to x plus 2. So y would be equal to 2 plus 2, which is 4. And y is going to be equal to x plus 2, so y is going to be equal to 6. So what we've got here, this point right here, that is going to be 2, and then we're going to have 2, 4. So 2, 4 is this one just here. And this one right here at the top is going to be the 4, and then we're going to have 6. So they're the points of intersection. In part C, we need to find the area trapped between the curve y is equal to negative x squared plus 7x minus 6 and the line y equals x plus 2, given our answer as an exact fraction. So what we want now is the area, and I'll just shade this in just here. We've got two different choices here in the way in which we do this. I'm going to do both methods and then you can decide what you like to do. The first method, the more generally used method, is to find the area trapped under the curve, in this particular case from x is equal to 2 to x is equal to 4. Then what we would do is find the area of the trapezium the line makes with the x-axis and take that away. So what I'm going to do is just set up the integral. So if we consider now the integral, let's just grab up a pen. The integral is going to be of the curve. We're interested in this, and I will just put that here now. It will be the integral from the points of intersection, so it's 2 to 4, of negative x squared plus the 7x minus 6. We're integrating with respect to x, so that is with respect to x, and we're going to subtract away from that now the area of this trapezium. So if we consider the trapezium, and I'll just draw it up, we've got a base, we've got a height, and we've got another parallel side and a height just there. So if I just connect this, the distance here, the difference in the x coordinates, 2 and 4, that is going to give me 2. We know that this y coordinate just here is going to be 4, so that will be 4. The y coordinate here is going to be 6. So if we just consider the area of this trapezium is 4 plus 6 divided by 2 multiplied by 2. So that's going to give us now an area of 10. So once I found now the integral here and put the limits in, we can subtract away the area of this trapezium, which is the part underneath. So let's go ahead. What we can do then is this integral. So if I just call this now the whole thing, let's just call that the area. Let's just call all of this now. So hopefully now that is what we're finding. I'm going to call this here A1. We can say now that A1, using this integral right here, so just getting that up, we can say now that A1 will be equal to, and I'm integrating. So if I integrate now negative x squared, I get to negative 1/3 x cubed. If I integrate 7x, I'll get plus 7 over 2 x squared. If I integrate the 6, it's going to be minus 6x, and we're interested in this now from 2 to 4. So substituting in what we're going to have, A1, the total area. If I just put this in, and I'll be quite lazy with this, I'll just put it through the calculator. Let's evaluate 4. So what we'll have then in here, we will have now, so let's just set this up and then I can swap it over. So we'll have negative now, and we're going to have 4. And the reason I'm putting it in brackets, I'm going to just swap this over for the 2 shortly, over 3. And then we're going to have now plus 7, then we'll have lots of the 4, which we're going to square, and divide by 2. Again, you can simplify if you like. Minus 6 lots of the 4, so that's going to go in there. That's going to give me 32 over 3. In an exam, I would show my full workings. We've looked at this in the past. And then if I swap that over and just go ahead and swap that for a 2, so instead of a 4, just put a 2 in, what we're going to have now is the area, the total area, by substituting in 2. So if we go ahead and do that, 2's going in there. What's that give me? So that's negative 2/3. So negative 2/3. So what we're going to get on here, if we just do this, A1, 32 over 3, subtract negative 2 over 3, that's going to give me 34 over 3. Therefore, we can say now that the area is going to be equal to A1 minus now the trapezium, so it's going to be 34 over 3 minus the 10. Well, that's going to give me now 4 over 3, and that is the area. So that's the area trapped between the line and the curve. There is an alternative way to do this, and it's slightly more mechanical. What we're now going to do is use purely, it's integration, pure integration to simply find the sliver here. What we do is look in the interval that we're interested in, which is 2 to 4. The curve is above the line. So what I'm going to do is integrate the line, the curve subtract the line. If I take the line away and integrate, then that is going to remove this part just here. So let's see what that looks like. What I'm going to have, I'm going to say now the area, the total area, and that's just going to be the sliver we want. And I'll just call that A2. A2 is just the sliver. That's going to be equal now to the integral from 2 to 4 of the line. The line is negative x squared Then we've got plus the 7x minus 6. So plus now 7x minus 6. And I'm going to subtract away from that now the line. The line is x plus 2. So let's just go ahead and do that. So x plus 2. If I had now, and we'll just write this in, so that's what we're going to have. If I had now, and it was the other way around, so for example, if I had a positive quadratic and the line was here, and we were finding this sliver here, well, in that particular interval, the line is above the curve. So we would do now line subtract curve to find the area that we're looking for. Here, we're doing curve subtract line. So I can say that A2 will be equal to the integral from 2 to 4. And you'll see this similar to our simultaneous equations earlier. What we're going to have is negative x squared. We've got 7x minus x, which is plus 6x. And then we've got now minus 8, and we're integrating with respect to x. So A2 is going to be equal to, and we're going to have now integrating negative 1/3 x cubed plus 3x squared minus 8x, and we're going to evaluate from 2 to 4. So let's do that. So we can say that area 2, which is just the sliver, well, that's going to be now negative 64 over 3. That's going to be now plus 48. Let's just sub in that. That's plus 48. And that's going to be minus 32. All I'm doing is evaluating here, just subbing in for 4. Then we're going to get now, we'll get negative 8 over 3. So this is just subbing in for 2. Plus now 12 minus 16. Okay, so let's just put that for a calculator. So what we'll have then is negative 64/3. So negative 64/3, and you can do this manually or in your head, entirely up to you. And then we're going to get on here plus the 16. That's what we have. From that, we're going to subtract now negative 8/3. So negative 8/3. So negative 8 over 3. And then we're going to have minus 4. And this will give us exactly the same answer of 4/3. So we can say now that A2, as expected, is 4/3, and I've simply used integration. So two different methods. You choose which one you want to do. Generally speaking, it's suggested in a textbook that you would do the first one, but it's your call on which one you want to do. Question number 9. Find the area trapped between the curve y is equal to x squared plus 2x plus 5 and the line y equals 5 minus x, giving your answer as an exact fraction. With any of these problems, a quick sketch will help you out, so let's go ahead and draw that. So what we've got then is a positive parabola. You don't have to draw this, entirely up to you. I'm going to do it just to give us some idea. So this one isn't going to cross the x-axis, so I could complete the square with this one. So y is going to be equal to x plus 1, so x plus 1 all squared plus 4. Okay, so this point right here, we're going to get this point. This is going to be the minimum, which is going to be negative 1, 4. We'll have a positive parabola, which will open up something like so, come round, look something like that. So this is this graph. Y is equal to 5 minus x. Well, that's a straight line. Let's go ahead and do that one. That's going to look something like so. And that is what we have. So we can see both of these. If x is 0, y is going to be 5. And with this one, if x is 0, y is going to be 5. So we've got this point right here. So this is 0, 5. So what we're looking for now is the area trapped between the two. So let's go ahead and just shade that in. That's this part right here. So my choices now are as follows. I can do the line subtract the curve, and that will find me this area. So when I say line subtract curve, we do the line, subtract the curve, integrate, and evaluate between the limits. What we need to do is just find the coordinates of this point right here. So yet again, with simultaneous equations, that's what we're going to do. So if y is equal to x squared plus 2x plus 5, we can say that x squared plus 2x plus 5 will be equal to 5 minus x. So finding this point right here, we can see now 5's are going to cancel, adding x to both sides. We've got x squared plus 3x is equal to 0. Factoring x, x plus 3 is equal to 0. we can see x is equal to 0, x is equal to negative 3. So this point right here, we've got an x-coordinate of negative 3, and we would have a y-coordinate now of 5 subtract negative 3, which is going to give us 8. So what I could do is find, again, the area of the trapezium. So if we look at this trapezium, the area of the trapezium can be found, and we can go ahead from this and subtract the area of the curve below here. So if we just look at this, this is one method. So what we've got, this length right here, well, that is going to be this here. And if I just draw this on, let's just put this on so we can see what we've got. This is the trapezium that I'm about to find. So what I'm going to do is find the area of this trapezium and then simply integrate from negative 3 to 0 the curve and take this value away, because the integral gives us the area trapped under the curve, which is just here. So what we've got, this length right here is going to be 3, that's going to be 5, and that is going to be 8. So area, remember this is the right angle here, it will be 8 plus 5 over 2 times by 3. So that's going to give 39 over 2, that's the area here. Okay, so if I just say now that this one right here is going to be A2, that is the area trapped under the curve. So if I just shade this in, this is what we're looking at. So if I now find the integral under the curve, then all I need to do is subtract this away, because then it will leave me with this sliver just here. So this area right here is what I'm going to do. I'm going to take that away, and then that will give us this bit right here. So what we can say then is A2, so A2 will be equal to the integral. Now we're looking at this from negative 3 to 0, so negative 3 to 0 of x squared plus 2x plus 5, and we're integrating with respect to x. So an expression now for this, well, it's going to be 1/3 x cubed plus x squared plus 5x, and we're going from negative 3 to 0. Okay, let's go ahead and do this. So A2, if I substitute in the 0, 0 plus 0 plus 0, then if we do now the negative 3, well, that's going to give me negative 27 over 3, which is negative 9. That's going to give me now negative 3 squared, well, that's going to be plus 9. Then we can have negative 15. So that gives me that A2 will be equal to, these are going to cancel, that's going to be 15 units. So all I need to do then is, if I want to, then I could call this part A3. We can say now that the area will be equal to 39 over 2 minus the 15, which is going to give us now, what's that, 9 over 2? Or if you like, 9 over 2, which is 4.5. So that's what we've done. So that's the first method. The second method is to integrate from negative 3 to 0. We have the line which is the 5 minus x, and we're going to subtract away now the curve which is the x squared plus 2x plus 5. So this is the second method, that I'm simply going to do this in a very mechanical way, such that I take the line and subtract away the curve. In this particular interval, the curve is below the line, so we do line subtract curve, and that's what we get. So let's tidy this up, integrate it, and look at what we get. So we can say now that the area, and that'll be the sliver, will be now the integral from negative 3 to 0. Okay, let's, the 5's are going to cancel. So what we're going to have here is minus, so we've got now negative x minus 2x, that's going to give me now negative 3x. Then we're going to have on here negative x squared. We're integrating this, so what are we going to get? So we can say that the area will be equal to now, that's going to be negative 3 over 2x squared, then we're going to subtract from that 1/3 x cubed, and we're integrating now from negative 3 to 0. This is just going to find us the sliver. So the area, well, if we consider what this is going to be, if I substitute this in, this is going to be now negative. So what are we going to get? That's going to be negative 9. So that's going to be negative, in fact we need to do 0 first, don't we? 0 plus 0 plus 0 to show I've done that. Then we're going to have now negative 27 over 2. And then that's going to be plus, and what are we going to get on here? If I substitute that in, that's going to give me now 3 cubed is 27. That's going to give me plus 9. So what do we get? We can say that the area is going to be now negative. So this is going to be, what's that going to be? Negative 9 over 2, which we can see now the area is going to be 9 over 2, as expected. So that's using the mechanical method. I've simply evaluated by taking the curve away from the line in the given interval and evaluated the limits being the points of intersection that I solved for simultaneously earlier. Your call, you decide on how you want to do it. Okay, question 10. The diagram below shows a sketch of the line y equals x and the curve y is equal to negative x to the 1.5 plus x to the 0.5 plus 1 for x equal to or greater than 0. In part A, the coordinates of a point where the line and the curve meet are 1, p. In part A, we need to write down the value of p. Well, this is just the line y is equal to x. So if we sub this in for part A, if y is equal to x, then what we're going to have is y is going to be equal to 1. Because y equals x, 1 is x, and y will be 1. So we can say, therefore, now p will be equal to 1, and we'll have the point 1, 1. It says the shaded region R is bounded by the line and the curve. We need to find the area of R. Entirely up to me on how I want to do this. What I'm going to do, I'm going to go back and I'm just going to find the area of this triangle, which is nice and straightforward, and then simply subtract that away from the area trapped under the curve from this point right here. So let's do that, and your call on it really doesn't matter. So let's just shade this in. So this area right here, let's just look at that. Now we know from here that this right here, the x coordinate here is going to be 1. The y coordinate here is going to be 1, so that's 1, 1. So if we look at that triangle, the area, so if we do that, this is what's going to be subtracted away from the integral. So the area trapped under the curve that we find using integration. So this is 1, this is 1. So we've got now base times height, 1 times 1 divided by 2, which is going to be 1/2. So what we can say then is R, the shaded region, will be equal to the integral from 0 to the point of intersection, which is 1. We're going to have now the negative x to the power of 1.5 plus now x to the power of 0.5 plus 1. Remember, we're integrating with respect to x, and then we're simply going to be subtracting 1/2 because that's the area of the triangle. So R, our integral. So we got 1.5, that's to the power of 3 over 2. So I need to raise by a power and divide by the new power. You can either use fractions or decimals. I'm going to use fractions. So we're going to have negative 2 over 5 x to the power of 5 over 2. This is to the power of 1/2 or 0.5. So we're going to raise that to 3 over 2. So plus 2 over 3 x to the power of 3 over 2. As stated, you can use decimals if you want. Plus, then we're going to have x. We're interested from 0 to 1, and then we're going to subtract away 1/2 at the end. So let's do that. What are we going to get? If we substitute in 1, we're going to get negative 2 over 5. 1/20 power is just 1. Plus 2/3 plus 1. And then we need to subtract away 1/2. Remember, I should really put in here plus the 0 plus 0 plus 0, as we need to evaluate that. But we're going to end up with 0 from there. So let's do that then. What have we got? We've got now negative 2 fifths. So negative 2 fifths plus 2/3, so plus 2 over 3. And then we're going to add to that now, what have we got? 1 minus half, which is going to be minus half or minus 0.5. And that gives us now, let's check all of that is in there. Let's make sure we've got this in. We need a plus here, don't we? It's not minus. We're going to have plus 1/2. Let's do plus 1/2. That's what we should have. And it's giving me 23 over 30. So let's just check I've got all of that in. 23 over 30. That looks pretty good. So 23 over 30 is going to be now my final answer. So that's left as an exact fraction, and that is the area of a region R. Do be careful with your negative values. As you saw, I nearly made the error. Fortunately, it gave me a negative answer. If it hadn't, I probably wouldn't have even questioned it. But that's now found as a value of R, and we can say it's an exact fraction at 23 over 30.